Okay. Uh, I think last discussion we are discussing the ratio test, but I haven't told you the root test. But probably we can start from this root test, giving you several examples, and then I'm planning to go for 11.7, but 11.7 is just a review. So I will review some problems for you, and then go to 11.8, the power series. So probably we'll start from here. Uh, the ratio test and root test. So we already have this ratio test. The other tests in 11.6 that quite similar. It's called the root test. Okay, if ratio test is finding ratio between uh, two terms of sequences, the root test is to to take a root, okay, to take a root of some sequence. Let me write this: if limit so all uh, the method is take the end root of some sequence, and it needs to be some L or any finite number. So if L is less than 1, then the series will be absolutely convergent. So it's quite uh, similar with the ratio test. Okay? So L is less than 1, greater than 1. So if greater than 1, it's divergent. Then if it's equal 1, then uh, same thing happen. It's inconclusive. It's we cannot conclude. Inconclusive. Okay, so how to use the root test compared with the ratio test? Ratio test, you can use it most of the cases, okay? But for root, every time you see any sequence or series that have power n, you can definitely use the root test. Okay? It's much more easier to be used for the power of n. for example, like that. We can definitely take the absolute value of the inside and then take the root of n, and then we can conclude the result, in which the result is just limit of the inside of the power of n, in which we can conclude that this is 2 over 3. It's less than 1, so it's solidly convergent. Okay. Okay, the other one is quite interesting. If you have a series n plus 1. Okay, is it converge or diverge? Okay, let me give you some thought to think about this second one. Can you use the root test? Okay, if you're using the root test, let me write the root test. It will be n plus 1, right? So if we are taking the limit of this formula, we will get what? 1, right? So here it's inconclusive. Well, what we can do? Let me write the an as, let me write the sequence first. Okay. First, if you can rearrange the formula in any way you want, as long as it is consistent and correct and logically it could be done. For example, you can write this as like that. Okay, and remember, if we have the limit as n approach infinity of n plus 1 over n with the power of n, what it's equal is the definition. It's equal E, right? Okay, you remember. So I can write here that as n approach infinity, then it will be, or let me write here, limit of 1 it's equal 1 over E. So and write as a conclusion, since this limit is different from 0, the series diverge. Okay, so my notes here, testing the series for convergence or divergence is often helpful if start with a divergent test. So from here, from 11.6 to the next 11.7, we will move to how we choose the method, which method we need to use, some strategy to help. Okay. Some problems will be, or it can be solved by several methods, but some they have some. Uh, it can be a pattern. It can be trial and error. Okay, so good experience if you try for several exercises, okay, by yourself. Okay. Have I put the PDF for exercise in Moodle? Can you check? If not, then I will, maybe later I will put another exercise. Okay, that's the ratio test, and basically ratio test is really helpful if you have this kind of power of n. Okay. So let me go through some strategy and then review for maybe 11.4 and 5. And if we still have time, we can review also 11.6. And maybe the end of the lecture, I will go to the introduction of 11.8. So 11.7, this is just a strategy how to choose the test. First is, of course, the divergence test. Especially if you can see if you have see the limit. If this is not 0, then it will be directly, we can conclude diverge, right? This first, second one is the P series. So if you have 1 over n with P, okay, P greater than 1 is convergent. P less or equal 1, it will be divergent. And third, if you can see the Geo Series. So this is just a reference. In several cases, you need to think faster to decide which method you need to use. So in Geo Series, if you see this or this, we know the convergence if this. Oh, wait, the R, sorry. It's converged, it's diverged. The ratio. And then if you can compare to another series, then you can use the comparison test. And you may also use the direct one or the limit. So right here, compare AN with the BN. And usually the other one is known series. Okay. And 5, the alternating series. If the form has the negative n or negative 1 and minus 1. Or let me write completely. And remember, from here, from the alternate series, you can have absolutely convergent, conditionally convergent, and the divergent. And the last, or no, the last two is the root and ratio. The root, if the form is, you can take the root. Okay. If the form is Bn n, right? Usually ratio involves factorial, usually, but not always. Or constant having raised by n power. Usually, okay. But my suggestions, the ratio test can be really helpful. But sometimes it can be quite long in the process. So you need also to choose wisely which method you can choose. Then the last one is actually the integral test. Because integration seems more complex, right? Because you need also to remember the method, how to integrate, and so on and so forth. So I put on the last number. Okay. Okay. That's the 11.7, the strategy. But maybe later we will have to use some exercise. Okay, let me review some parts. Let me give you some exercise. So determine the series converge or diverge. Okay, first is 1 over ln n. The second one is 1 plus cosine n over e to the power of n. The last one is sine 1 over n. The first one is from n equal to, because if you start from 1, it will be problematic. Okay, can you try? I will give you several minutes. Okay, so I was mentioning before the divergence test, right? The divergence test. What you need to remember, the divergence test is just a first layer to test the series. Okay, and if you find if the uh, actually what divergence test means or define is if the series of A n converges, then its limit is equal 0. So you need to prove the first one and then going to the second one. If you are looking at this series, by looking at this, maybe you will conclude that the series is equal 0, right? But actually, what the divergence test in definitions, the if is say that if the series converges, then the limit is 0. It's not if the limit is 0, the series converges. It's not like that. So you need to start with the if the series converges, then the limit is 0. Okay, and if the limit is not 0, then it's divergent. So it's quite tricky in words. So if you don't if you mix up the definitions, you will mix up in the problems. So what my suggestion is, you can try definition tests, but after you try definition tests, try another method that you think it's also simple. And then if there is no contradictions, then your assumption is correct. Okay, that's how you can do it. Because maybe the problem can be any random problem, right? So first, maybe the first layer you can do the definition test, and maybe you cannot conclude anything. Oh, I cannot conclude from here, so you need to take other tests. Okay, like from here, the other test that can be related to this A is you can compare this. You can use the comparison. So if you have 1 over ln n, then maybe you can just compare with the 1 over n, right? Because 1 over n, you know the series. If the series start from 2 until infinity, it will be diverged, right? It will be diverged with the p series, right? Or if you maybe start from ln n, it's of course is less than n, right? So 1 over ln n is greater than 1 over n, okay? Because this is already diverged. So another layer that higher than diverge is still diverged, right? So this also diverge. So we can conclude also diverge by comparison test, or if you want to completely say that this is the direct comparison test. Because the question is only asking its converge or diverge, whether you find it's converge, you don't really need to find the value. You don't really. You just need to find the proof. Okay, with some assumptions, it is also okay. If you want to start with some assumption, and then you prove that the assumption is correct, and that's still okay. So probably the way you see this chapter 11 is how you decide to take which method you want to use and how to think logically. Okay, and you are actually learning how to take decisions, right? It can be very helpful not only for the courses but for your life also. And the other one, it's the 1 plus cosine n divided by e to the n. Every time you see it is just my preference or my suggestion. If you see the cos or sine in a really simple form like this, it seems so it's really trouble, right? This cosine. Okay. If you look at just 1 over e to the n, probably you can take the comparison test as well, right? Because you know the cosine, the maximum is 1, or sine is also 1, right? So whenever you see sine or cosine in a fractions like this, you can think definitely go to comparison. It's way faster, okay? Unless it takes some a little bit complex, okay? So you can observe the 1 over e to the n. So you can look at this first from 1 to infinity. Or not 1. Let's just say 2 because cosine can be 1, right? So 1 plus 1 is 2. Okay, let's say 2. Okay. If we want to break up this or expand the series, it will be 2 over e plus 2 over e squared plus 2 over e cubed and so on, right? You will notice that it will multiply by 1 over e. Or we can conclude that this is our ratio. Okay? This is actually the geometric series. Okay? And the ratio here, 1 over e is less than 1, in which in the geometric we call this is convergence. The series is convergent. And then, because 1 plus cosine n will definitely cannot cannot be higher than 2 over e to the power of n, then we can conclude that the series is also converged by direct comparison test. Okay. Now, the third one is quite tricky. Anyone find anything or idea? You find something? Let me see. What do you think is diverse? Oh, okay, okay, okay. Yeah, it's actually diverse. It's actually diverse. But what I want to show you is from here. Uh, because inside is 1 over n, let's observe the 1 over n. We know this is diverged, right? From the P series, right? And here, we can use the limit comparison test. The limit comparison test. So sine. Okay. Okay, now you need to see that I can exchange this. Okay, let me write where. Let me write here. Uh, let the 1 over n equal maybe theta. So limit as uh, or maybe oh yeah, correct. So as the theta going 0, this is equal 1. Remember from the limit comparison test, if you find some number, it can be both converged or both diverged. Okay? But here, because we know that this this series here is diverged, then it's also diverged. Conclusion: the series diverge by a limit comparison test. Okay, this is what we learn in calculus 1. That is, if you have limit as x approach 0, sine x over x equal 1. The definition. And you can also apply the same with the tangent. Also, if you want to change the cosine, you can also, but you need to rearrange the formula. But the basis is the sine x divided by x is equal 1. Okay, so limit comparison test also useful. Okay, the comparison one. Let me give you maybe a couple more questions and we move to 11.8. So I think this 3 questions is mostly the comparison, the 11.4. Okay, so this is 11.4 mostly. Okay, yeah, I think all of them you can solve by 11.4. Next questions is I think from 11.5. Yeah, let's try another one. So determine the series, whether it's absolute convergent, conditional convergent, or divergent. Start from this simple one. And then okay, 3 questions here. It's focused on the alternate series. But not really alternate. One of them is not alternate series. Let me give you some couple of minutes to think. That's okay. That's you win.
I need some breath.
You win. Don't forget to state the conditional convergent and absolute convergent at the conclusion. If it's diverge, diverge, but converge can be conditional or absolute convergent. Yeah. Okay, let me start from the number A. Okay. So this is the alternate series. Okay, so if this is the AN, let me define the BN is the absolute value of AN. Okay. So I will start from the BN first and then back to AN. So if you see BN is the absolute value of the series. It will be the series of 1 over n with the power of 2 over 3. Okay. And we know that Bn is decreasing, right? And the limit, or maybe I will write it here, is Bn plus 1 is less than Bn. And the limit of n approaching infinity of the 1 over n is equal 0. Okay, from here, we can say by alternate series, it's converged. But okay, the series itself, if we take the only the Bn and try to determine the series, this is P series, right? And P is equal to over 3, it's less than 1, in which this is divergent or diverge. Series diverges. Okay. So we have converges for the alternating series, that the absolute value is diverges. So the conclusion is the series is conditionally convergent. So conditional convergence is mostly happen in the alternate series. So the alternate series itself, if it is converged, the absolute value can be diverged. So when that happens, that's conditionally convergent. Okay. So first, this part is we determine the alternate series. Okay. There's only two requirements. You need to find that the terms always decreasing and the limit is equal 0. When you find these two, you can say that this is convergent in alternate series. Okay? But of course, because it's alternate series, you also need to think if it is without the negative part, or you need to make the absolute value of the series. Okay, so then you need to also to consider the series of the absolute value itself. So it's converged, but it differs in its absolute value. So we say it's conditional convergent. Okay. So absolute convergence, conditional convergence, it's mostly happen in the alternate series. Okay. Okay, the number B, let me move down here. -1 with the power of n, that's the alternate sign. If we take the absolute value, it will be equal 1 over n squared plus 1. And we can look at this 1 over n squared. This is the P series, right? With P is greater than 1, in which this is converges. And if we observe the alternate series, we know that the Bn plus 1 is less than the previous terms. And the limit of the series, is the sequence in the series is going to be 0, in which we can say this is also converged. So we have converged in its alternating series and also converged in its absolute value. So we have double converged here, right? We say here the conclusion, the series absolutely convergent. And because it's absolute convergent, of course, the whole series is convergent. Okay. Okay, that's number B. And number C is negative n divided by n squared plus 1. Anyone got results from this relation? I think I read some of you read it's diverge. It's diverge. Okay, so first, what we can do is we can rearrange and look at this part first. Okay, so we take away the negative sign, not take away, but factorize outside the sum. So we can focus on the sum, the positive one only. And consider, let's say this is an and bn is 1 over n. And then let's use the comparison of an divided by bn. What I want to do is I want to make the top of the an become n squared. Okay. So this will be n squared plus 1. And then we know that from this limit, it's equal 1. And then since the series of 1 over n diverge, then this also diverge. By limit comparison test. And the negative also diverge, since the whole thing in the positive one diverge. Okay. Okay. that's some review. Maybe the other exercise, maybe your TA will come up tomorrow with some exercise. But the next section is the 11.8. I will start go there. Let me just skip this first. Any question from the questions before? Okay. If you need any help after class, you can talk to me. So it's called the Power Series now, the 11.8. Okay, so what we did before, or the other testing method and so on. So what we did before, testing the series of AN, right? Now we consider our series. The terms, okay, the terms include a power of variable x, or we could say we write the series Cn xn. Okay. C is the constant, okay, the constant, and n is the terms, okay, in the sequence series. So we will have a constant and then the x. Let me write the general form first. Okay, so usually in the power series, we start from 0. Okay, we start from 0 because we want to make this x become 1 first. Okay, so we start from the first, just a constant, and then the variable x squared, x cubed, and so on. So we start from C0 plus C1x, okay, plus C2x squared plus C3x cubed, and plus until infinity. Okay. Okay. So for example, if the Cn equal 1, okay, then this is just xn. It's 1 plus x squared plus x cubed plus. Okay. And we know that this is the Geo series, which R is equal x, right? And the convergence is start when ratio is less than 1. Or we can say that this is in between -1 until +1. So this is converge, and the first one is greater than 1. Greater equal. Or we can also write this as in terms of fx. So the f is having infinitely many terms. Okay, but let's back to here. If we put x equal half, n, sorry, it's half with the power of n. To start from 1 plus half plus, okay. And we know this is converge, right? The Geo series converge. If we put x equal to 1 plus 2 plus 4 plus 8 plus, it's diverged, right? Okay. So because there will be some x will converge, some x will diverge, we need to have more general forms in the power series, okay? And the general forms, so generally power series should be Cn and x minus a to the power of n. And then it starts from C0 plus C1 x minus a plus C2 x minus a squared plus C3 x minus a cubed plus, okay. And this is more general form. So this is called power series in x minus a. Okay, because we know from before the x can be diverged at certain points, and it can be also converged at certain points. So our goal here is later we need to define in which x is convergent, or we say it's the radius of convergence. Okay. But that will be the next one. And we called also the x minus a is the it's centered at a. Okay. So around a, the x will have some convergences. Not all x will be converged, but some x will converge around the A. Okay. For example, okay, let me give you some example. For what values does this series, let's just start from here. Okay, so if the let's define the AN as the sequence, and we can go to the ratio test. We can, and this is, so this will be n plus 1 and x minus 3. Okay. So as the n approach infinity, we get the x minus 3. So by ratio test, to be converged, this x minus 3 should be less than 1. Okay. So -1, or let's just 2 until 4, right? So we get this x for the convergence, and diverge when x is less than 2 and x is greater than 4. Okay. So it's actually most of the cases, okay, when you try to find which values of x that will be converged, most of the time you'll be using the ratio test, and then you will look for the x values here. Okay, and you need to make sure that this will be converged. Okay. So it's like in inequality, okay, like inequality. Okay, let me go for another example and then some conclusions, and maybe we can finish these sections. So for what values of x? Let me try one more time here. Of the series Okay, so n factorial and then x with the power of n. And here, same thing. We go to the ratio test. So we can cancel the factorial, cancel this. So it will be just n plus 1, and then just x, right? And if we plug in the limit, it will be infinity. So by this limit, okay, so when x is not 0, it will diverge, right? Of course, because the result for the limit is infinite. But when x is 0, it will be converged, right? So the only way uh, the only way to be converged. Okay, one more example, and then we can conclude what we can summarize from all these three. The question is the same for what values of x for the series to be converged. Okay, again, use the ratio test. This will be cancelled. So x, and this will be cancelled also. So limit, or let me just write a okay, we need to solve this. This, right? The factorial. Yeah. We can cancel this, and we get the result is okay. Now, as the n approach infinity, x will also going. It's going to be 0, right? So what will happen? So by ratio test, series will be converges for all x. Okay. So the first example, when you have some value for x, you can define x in certain value for the ratio, and for this one, if this is going to be diverged, if the n is going to be diverged, then when x is 0, it's the only way to be convergent. And when you get all the results, the limit of n is 0, then the series will be converged for all x. Okay. Now, the conclusion I will write here. The conclusions. The theorem for our series. Series converge when x equal a. Number 2, series converge for all x. Number 3, there is a positive number that series converges if x minus, it should be in the absolute value. Sorry. And diverge if r is the radius of convergence. So it means the radius of convergence is the interval when the series is convergent. Okay. So 1, 2, 3 is the case from all the example previously. So it can be converged when x equal a, and series can also be converged for all x. So it is 3 possibilities. So it has 3 possibilities. So it depends on the result on your ratio test. So it can be converged for all x. It can be converged only when x equal a. Like before, we state that it's converged when x equals 0. So that's the only way to be converged. Or it will be converged in a certain interval. Like I think the x minus 3, this one. at certain interval, it can be converged. Okay, and this is if the limit is 0, the limit of n is 0, the result 0, then all x will be converged. Okay. So that's why we get these three possibilities. Um, we will learn more about this and how to visualize the convergences and maybe some key points on how you look at the series. But I will talk about that next week. So I will just stop here now. Okay. Okay. Any questions? Yeah, we still have 11.9 and the 11.10, and 11.11. I will skip that. Yeah, I think I will skip that. Okay, if there's no other questions, then I will stop up until here, and we will discuss more about this next week.